Hi everyone. This video is intended to give a really quick introduction to the most common model for friction that you'll see and that we'll work with in class. This is a simple model. It's not the most accurate model, but it is pretty good, and it provides a way to get into some of the specifics of problems with friction that we haven't been able to do so far. So the basic premise of the model is that there's two types of friction. There is static friction and kinetic friction. And I'm going to break down each case. Static friction is the friction between two surfaces that are not moving relative to each other, while kinetic friction is the friction between two surfaces that are moving relative to each other. So let me talk about static friction first. So first, static friction. And as I just said, this is friction between two surfaces that don't move relative to each other. So what does that mean? Well, we've seen an example of this on the most recent problem set. So if you think back to problem 1 on that problem set, there was a block on top of another block on the ground. And I'll call the bottom block block A and top block block B. And in the problem, the two blocks move together. There was some push on the bottom block, and the thing that moves the top block is friction forward. And I'll denote this friction sub S for static friction. And then we also had this frictional force in the opposite direction on block A. These blocks slide together, and that's the key here. So even though they're moving, they're not moving relative to each other. That means that this is static friction between the blocks. So static just means not moving, just the normal meaning of static. So static means those two blocks aren't moving relative to each other, so there's static friction. The typical model that we use for static friction is that the static friction is less than or equal to this thing, that's a mu, it's a Greek letter, mu sub s for the coefficient of static friction, times the normal force between two surfaces. So this is the normal force, and that's the normal force between the two surfaces in contact. So in the example above, it would be the normal force between the two boxes that it's exchanged at this surface, not the normal force with the ground. That's important. And then this thing is called the coefficient of static friction. And this is a unitless number that tells you essentially how strong the friction is between two surfaces. It's all of the information about what the surfaces are and how they interact with each other is lumped into that number. What we're saying is that the frictional force between two surfaces depends on what the two surfaces are, what their material is, what their material properties are, like temperature and stuff like that. That's all lumped in mu sub s. But also it depends on how hard those two surfaces are pushed together. So if you imagine that B is heavier, if you imagine that B is a heavier block, it will push harder into block A. The normal force will be greater, and the frictional force on B and A will be greater too. If I pushed down on block B, therefore pushing it harder into block A, that would increase the normal force, and that would increase the friction between those two blocks too. And I think that's kind of intuitive. If you push two things together, they're kind of harder to move apart from each other, harder to move relative to each other, to slide along each other. So that's the frictional force scaling with the normal force. And then this is an inequality, and I want to highlight that because it's really important. So this means that static friction will be whatever value it needs to be to prevent motion up to some maximum value, where that maximum value is given by the coefficient times the normal force. So static friction breaks and things start sliding when the frictional force is equal to mu s times n. That doesn't mean that the static friction is always equal to mu s times n. It just means that if the friction required to keep two boxes or two surfaces from moving relative to each other is greater than mu s times n, then they'll start sliding. If so, let me give you an example of this. So let me scroll down. So let me leave the model right there. So let's say I have a relatively simple example to reduce the complexity of the problem. So let's say I got a block, 5 kilogram block, and I put it on a tabletop. And I push on the block, but the block doesn't move. So I push it this way. There's some gravity acting on it. There's some normal force that's keeping it from falling through the table. I push on the block, it doesn't move. That means that there's got to be something opposing my push. If the block doesn't move, then I know that there's some static frictional force opposing my push, opposing the intended sliding between the tabletop and the block. And also, if the block doesn't move, then I know that if the block doesn't move, I know that the push has to be the same in magnitude to the static friction. Because if my push was greater than static friction, the block would start to accelerate. If the static friction was greater than my push, that would mean that the block would begin to accelerate to the left, which doesn't really make sense. Because how could the static friction create motion? It wouldn't do that. All we know is that these two forces are exactly equal to each other. But let's say I keep pushing. I keep pushing harder and harder. I push harder. And when my push equals 40 newtons, the box begins to slide. So if I push harder, and eventually I push hard enough that the box begins to slide, how hard I was pushing right when the box begins to slide tells me that I reached the threshold value for the static friction. So that is when my push is equal to 40 newtons and the box begins to slide, that's when static friction is equal to its maximum value. That's the threshold value for the static friction. If I push harder than that, I'm pushing hard enough to make the box slide. If I'm not pushing that hard, I'm not pushing hard enough to make it slide. So that's the threshold value. So I could use that threshold value to find what the coefficient of static friction is. The normal force here is just equal to the weight. So taking G to be 10 for simplicity, the normal force is 50 newtons. So at that moment when I'm at the threshold, then my push, 40 newtons, is equal to the maximum value of the static friction, which is mu s, which I don't know, times the normal force, which is 50. So that means that tells me that the coefficient of static friction between these two surfaces is 40 over 50 or 0.8. That's a completely reasonable value for static friction. I'll note that this number is unitless. This is unitless because it's a ratio of two forces. It was the ratio of the normal force to, the ratio of my push force to the normal force here. So it was the ratio of the force required to get this thing to move over the normal force. That's a unitless quantity. And in that number, in the 0.8, the 0.8 is describing like all of the material interactions between the tabletop and the box here, which could be extremely complicated, but we're boiling all of that down to one number. And that number should be the same as long as I'm using the same box and the same tabletop. If I'm using a different box and a different tabletop or two different materials, that number will change. So this number, that number 0.8 is dependent on specifics, dependent on this specific situation with these specific materials. And that number will change. It'll be different if the box was made out of something different or the tabletop had a different surface on it. Okay, so that's static friction. And there's this threshold concept in static friction. So once I start pushing harder than static friction can take, then I can get the box to start moving. Now I'm dealing with a box that's sliding on the tabletop, and that sliding action produces kinetic friction. So let me scroll down here. So the second case for friction is kinetic friction. So this is when, this is the friction between two surfaces that are moving relative to each other. So friction between two surfaces moving relative to each other. So that is a block sliding on a tabletop, for example. So if I redraw this picture, now let's say I've got the same block, but now it's sliding on the tabletop. So 5 kilograms block on the tabletop. Now this block is sliding with some velocity. Now I've got kinetic friction. The model for kinetic friction, and let's say I'm continuing to push it this way to the right, and now there's some kinetic friction, F sub k, that's trying to prevent that motion or working against the motion of the box. So the typical model for kinetic friction is an equality, not an inequality. Now I have a coefficient of kinetic friction, which in general will be different than the coefficient of static friction and will be less, times the normal force. So it kind of looks the same. A few things I want to point out. This is the coefficient of kinetic friction, which is different in general than the coefficient of static friction. And this is an equality. So Fk always has the same value. There's none of this threshold business as there was for static friction. If two surfaces are sliding relative to each other, then there's kinetic friction, and that kinetic friction is always equal to mu k times m. So I could find out what mu k is in this situation. So let me make up some numbers. Let me say that when I push, in this case, when I push, so remember that now it's sliding. So when I push with 30 newtons of force, the box slides at constant speed. So if the speed is constant, then this means that acceleration is equal to 0. And that means that the net force is equal to 0, which means that the push has to be the same as the kinetic friction. So that means that when I'm pushing with 30 newtons of force, the push is equal to Fk. So that means 30 newtons is equal to mu k, which we don't know, times the normal force. This is the same box with gravity equal to 50 newtons and the normal force here. So the normal force is 50 newtons too. That means that mu k equals 0.6. And again, that's a unitless number because it's a ratio of forces here, how hard I'm pushing to the normal force. note that this is less than mu s. And in general, mu k will be less than mu s. Mu s will, like, kind of, the two surfaces are stickier when they're not moving relative to each other than they are when they're moving relative to each other. That's what that says. So that's an example of how you would use this model. It's really useful to know that the friction scales linearly with normal force. And that'll turn up in some of the problem solving that we do. I think the things that I want to say before we break here, just a few things to recap. In general, the coefficient of static friction is greater than the coefficient of kinetic friction. Wait, let me write this down. Okay, so a few things to note. So in general, mu s is greater than mu k. In general, area of contact does not affect mu, which is kind of counterintuitive if you think about it. I'll just say it does not affect friction, which is quite counterintuitive if you think about it. It seems like maybe a larger area would create more friction, but in fact, if you have two objects with the same weight but different surface area, the object with smaller surface area has its weight concentrated into a smaller area, and the object with a larger surface area has its weight spread out over a larger area. So you actually don't get really anything when you add the area, you just spread your weight over a larger area. And we could talk more about that. In general, mu s and mu k have to be found experimentally. You can't really figure out what they're going to be beforehand. You just kind of have to test it, maybe using setups like the problems that I showed earlier in this video. It's really hard to predict these things. They're really, really complicated. And also, the last thing to keep in mind in the back of your head when you're doing this, this model is simple, which is good in some ways, but this simple model sacrifices accuracy. So if you really want to get into it, you can find lots of literature on friction out there in the wild. And friction is crazy. It's incredibly complicated. And that complexity is really rich. And the models you can use for friction are really complicated. But you can do pretty good with the model that we have here. And it's worth it because the model is so simple to use that we don't lose that much. It gives us a picture in our heads of what friction is doing, and we can use it in problem solving. So we're going to go with these models, and just as a final reminder, static friction less than or equal to mu s times n, kinetic friction equals mu k times n. Those are our two models for friction. So hope that was useful, and I'll see you soon. Bye.